So last time we finished the proof of this theorem due to Rasborov and Smolinski, showing that if you look at constant depth Boolean circuits, so ACC0 together with mod Q gates, then to compute mod P value or mod P function, you will require exponential size. Okay, so constant depth would need exponential size. Note that if you allow more than constant depth, then in log depth you can compute it efficiently in polynomial size, but in constant depth you will require exponential size. So this was, the tools were very interesting and new. So we finished the proof. We learned that ACC0Q has low degree approximators, which are polynomials, and we learned that mod P has high degree approximators. It does not have low degree approximators. Okay, so now we will move to the next topic, which is again a lower bound for Boolean circuits. So this will be for the model of monotone circuits. So what is a monotone circuit? So it's a Boolean circuit if it contains only and or gates. Okay, so monotone means that there is no NOT gate. So these circuits, in the absence of Boolean circuits, in the absence of NOT gate, are called monotone circuits. And what can they compute? So a monotone circuit can compute only monotone functions. So monotone function, as the name suggests, it means that in the input, if you increase the input, then the output can only increase. What does increase mean? Increase means that if you, in the input, if you make any bit from 0 to 1, okay, then in the output it cannot happen that 1 becomes 0. Okay, so 0 can become 1, but 1 cannot become 0. So monotone means that it is increasing in one direction or it is decreasing. So if you decrease the input, then the output cannot increase, and if you increase the input, then the output cannot decrease. Okay, so input output, there is this relationship. This is because there is no NOT gate. So for x, y, n bit strings, we define x less than equal to y if for every bit, ith bit, xi is less than equal to yi. Okay, this defines what we mean by less than equal to for strings. So bit by bit it should hold. A function n-bit function, Boolean function, is called monotone if for every x less than equal to y, the same relationship holds for the output, for the value. Okay, then we say that it's monotone. So what you can show is that monotone functions always have monotone circuits, but they will in general be, circuits will be very large, but they do exist. That you can show. Has some monotone circuit. In other words, all the monotone functions can be expressed as monotone circuits, but the problem is that representation may be large. Okay, so for n bits, you might require 2 raised to n gates, 2 raised to n size, but it exists. On the other hand, non-monotone functions cannot have monotone circuit. So this is actually an if and only if. There exists a monotone circuit. So let's think of a monotone function which seems hard. Consider a hard monotone function, and a good example is this NP-hard problem called K-Clique. So this function is it takes n choose 2 bits in the input and gives output a single bit that on a graph G is 1 if and only if G has a K-clique. Which is K-clique means on K vertices a complete graph. So if you remember your theory of computation course, K-clique is, or algorithms course, K-clique is supposed to be an NP-hard problem. So it is supposed to be very difficult to solve practically. Okay, so here K is something which is also growing. So the brute force algorithm is that in this graph you have to look at all possible subsets of K vertices, okay, which will take time n raised to K, n choose K. So that is a lot of time. So this we believe is a hard problem. So this clique is a hard function then. So if it is believed to be hard in general or for an algorithm, then it would imply that the Boolean circuits, well, it won't imply, but then you will also believe that the circuits also will be large size, and hence you will believe that the monotone circuits will also be of large size. So well, first you observe that that's the important point why I took this example. The point is that clique is a monotone function. Why is that? Well, because in a graph which is the input, if you add more edges, so if you add more bits in the input, or if you add more vertices or edges in the input, then it cannot happen that a clique which existed before, a K clique, disappears. Okay, so the clique can only improve, it cannot disappear by addition of more edges or vertices. So this is a monotone function, and the question is, does there exist a polynomial sized monotone circuit for clique? Okay, so what about its monotone circuit complexity? So this is the question which we will answer negatively. Okay, that monotone circuit complexity for clique is indeed exponential, but the same question is open for Boolean circuits and for algorithms. So we'll basically prove this theorem by Rasborov. So pick your k to be a variable function of n. Say you pick it to be n to the 1/4, and then the k clique problem or k clique function. So there does not exist monotone circuit of size smaller than n to the square root k by 20 computing clique. Okay, that's the theorem, that monotone circuits for clique problem have to be of size n to the square root k, which is very large. K is like n to the 1/4, right? So this is something like n to the 1/8. So this is what we call exponential size. So it's an exponential lower bound. Okay, this is really an exponential lower bound on clique, but in the monotone circuit model. So how will we show this? This seems to be a pretty strong result, right? So first we have to understand two things. We have to understand properties of monotone circuits, right, which we can use. We have to somehow show that monotone circuits have a weakness, and then at the same time we also have to show that clique is a hard function. Okay, and then the two things we have to match. We have to show that monotone circuit is a weak model, and we have to show that clique is a strong model, and then we have to compare the parameters of the two. So what is that parameter, or what is that potential function that will give you a separation? So we'll use here the probabilistic model, right? Again, we'll use probability like we used in ACC 0. So using the probabilistic method, we will show that any monotone circuit computing clique can be approximated So like in the previous result, we showed that they can be approximated by polynomials, low degree polynomials. Here we will show that they can be approximated by an OR of few clique indicators. Okay, so instead of polynomial, we will use something else here. We will remain in the Boolean word or in the word of propositional formulas. So it can be approximated by an OR of few clique indicators. So clique indicators will be simple functions, low circuit complexity functions, and they will be few or of few. So overall, this monotone circuit model will imply that somehow it will imply a weakness of clique. Okay, so this is the weakness part. On the other hand, we will also show that clique is actually not weak. Okay, so when you match the two, then you will get the lower bound. But let us first define what is a clique indicator. So for a subset of vertices are 1 to n. So for a subset of the vertices, let clique indicator Cs be this Boolean function. So it takes a graph, which means edges, and choose two edges. By the way, you can assume it to be an undirected graph. So there are an undirected graph without self loops. So there are exactly n choose two edge possibilities. So that edge vector is given to you, defines a graph uniquely. Now in the graph, you test whether S, the vertices S, form a clique. So 1 on G if and only if S is a clique in G. Okay, just test this. And this is called, CS is called clique indicator of S. And as a notation C phi, so for the empty set, when you don't take anything, you assume it to be a clique of size 0. So conventionally we can set C phi to 1, and for all the other non-empty subsets, look for a clique. I mean, check whether there is a clique on the vertices defined by the subset S. So what is immediate from this is that the clique function, this is an OR of clique indicators go over all the subsets of size k. Right, so this follows from the definition of clique, because clique Kn will be 1 if and only if there is a k clique. If there is a k clique, then there would be a subset of k vertices, and that would be S. So Cs will be 1, and it's an OR. So if one of these Cs is 1, the answer is 1. Right, so this follows from the definition. So this is what was meant by OR of clique indicators, and the weakness of the monotone model would mean that, or we will show that clique actually can be approximated by few of these CS. Not all CS are needed, just few will be enough. So first we show a lower bound on the number of clique indicators. On the number of S needed to compute clique. So in fact, we will use a simpler input than a general graph. So we will use yes instances to be very simple graphs or very simple input instances. So they will basically just be randomly chosen k cliques. Okay, no other edges. Those will be the yes instances. So let us define two simple distributions. On n vertex graphs. So first is for the yes instances of input. So this distribution is on a random subset big K of size small k. So on a random subset, output a clique. And no other edges. So these are the yes instances. So yes instances with unique k clique. And what is the no instance distribution? So the no instances that we will focus on in the proof are, you want clique to be, k clique to be absent, right? So how do you avoid that? So this is non-trivial. It's a more clever construction than the first one, or more clever definition. So what you do is on a random function, that is k minus 1 valued on the vertices. Okay, so every vertex you randomly assign a label 1 to k minus 1. Okay, so now you have basically clustered the vertices in k minus 1 clusters in a random way. And what is the graph that you define? So UV is an edge of the graph. If and only if the labels are different. So basically you have these k minus 1 clusters, you join across. Okay, so this is a k minus 1 multipartite, k minus 1 partite graph. So these are no instances. So you are just outputting a random k minus 1 partite graph. Can it have a k clique? Well, it cannot have a k clique, right, because there are only k minus 1 parts, but it has a lot of k minus 1 cliques. Right, if you pick vertices 1 each from each of the k minus 1 parts, then all possible edges are present. So you can immediately see that clique function is 1 on the yes instances and 0 on the no instances. Right, on the yes instances there is always a k clique. On the no instances there is never a k clique, but there are k minus 1 cliques. So these are your yes and no instances. So let us first show that clique is hard. So basically what we will show is that clique requires many indicators. It will suffice to show that on one indicator, if you just use one indicator, then the yes instances with high probability will fail, which means that your indicator will output 0 on yes instances and the opposite thing on the no instances. So on most of the no instances, your clique indicator will say yes. Okay, so the answers will be wrong with high probability. This is what we want to show, which will mean that you need many clique indicators even to work correctly on yes and no distributions as defined above, as defined here. So if k is, let's say, n to the 1/4 and S is a subset, k size, then either the probability on no instances or being 0, the indicator saying 0, which is the correct answer, that probability is quite small, or on the yes instances saying 1, which is the right answer, is extremely small. Okay, so either on the no instances there will be mistake, but this mistake is only 1%, or this mistake is actually 99%, right? So on 99%, 0.99 fraction of the no instances, the answer will be 1. So this mistake is more than 99%. But in the yes instances, the probability is exponentially small. So almost everywhere it is making a mistake, right? So second thing is a bigger problem, which shows that clique is actually hard for or of indicators. So let us show this. So we'll use some probability. So denote, we'll use a parameter L, root k minus 1 by 10. So suppose the set S is smaller than L. So see, either the set S is of size less than L or more than L. So when it is less than L, it will make mistake on one side, when it is more than L on the other side. So for example, when the set S is of size less than L, it's a small set, then what will happen is, then we have to look at the no instance distribution, right? In that distribution, although the k clique is absent, since there are so many k minus 1 cliques, this indicator will usually answer 1 because the set is small. And when the set is large, then we'll show that mistake happens in the other side. So remember that S is your, S defines your clique indicator, right? So if you take a small set, then you will have these false positives, you may say. And if you take your indicator to be large S, based on large S, then you will have the opposite problem. So we'll do it step by step. So let us first handle this small S case. So a random, what happens when the set is small is that, or your indicator is small, is that a random C from S to k minus 1. So when you label this set S using 1 to k minus 1, this will be 1 to 1 with high probability. What is the probability? So the first element in S you can freely label, but then the second one you cannot use the label which you used in the first vertex, right? So that will be 1 minus 1 less label, and third one will be 1 minus 2 labels less, and so on till L minus 1 labels less. Okay, so what is this? How big is this? So this is at least 1 minus the sum which is at least 1 minus L square over k minus 1. L square over k minus 1, by definition we have picked it to be 1 over 100. So you get 0.99. Okay, so almost always your random labeling will keep S distinct. The labels will be distinct, which means that in the k minus 1 partite graph, you will see a clique on S, right? So your answer will be 1, but there was actually no k clique. So your answer is, so for 99% of the cases, your answer is incorrect. So vertices S in the no instances form a clique. Which means that the clique indicator will answer 1 with high probability on no instances. That's one case. Okay, let's go to the next case. When the set is large. So basically you have chosen a big indicator. So now what will happen is you might be missing now yes instances because you have chosen a bigger indicator. So let's check that. So the probability of S being a clique in the yes instances, let's calculate that. So S will be a clique only when this graph of in the yes input distribution, it is contained in the clique, right? So yes input instance, this G is already a K clique. So S has to be a subset of that if you want to see a 1 in the answer. So this is the same as the probability that S is contained in this big K subset, the way G was defined. Right, so graph G was defined by with respect to some subset big K of size small k. S should be contained in that subset of that if you want your indicator to say to output 1. And what is that probability? So given an S of size more than L, well, in fact we can first give the exact probability, which is you want to pick a random subset big K, but you also have to put big S in it, right? So that is total number of choices is n choose K, and favorable ones are n minus set S, K minus set S. Right, which is less than equal to n minus L, K minus L divided by n choose K, which is less than equal to n choose K minus L divided by n choose K, and that is exactly with the binomial coefficient expansion K minus L plus 1, keep increasing it to K and n minus K plus 1 up to n minus K plus L. So now all the numbers dividing the numerator, is K minus L plus 1 to K, they are smaller than, they are at most K. So you get K raised to L as an upper bound. All the numbers that appear in the denominator, they are at least n by 2. So you get this 2K by n raised to L. What is K by n? So K by n is like is smaller than n raised to 1 by 4 divided by n, right? So n raised to minus 0.75. So all this is certainly smaller than n raised to minus 0.7 L. And what is L? L is root K by 10. right. So you get smaller than minus root k by 20. Okay, so in case 2 you get success probability or the error probability to be very large on yes instances. In case 1 you got error probability to be large on no instances. Okay, and you can see the probabilities match our claim. So what we have shown is that OR of smaller than, so actually maybe we will give the proof. So we will actually use the above lemma 1 to show that if you just take n raised to root k by 20 or fewer than that indicators, it cannot be clique. So this almost immediately follows, but let us just do the formality. So first you write clique as this OR of clique indicators I1 to m, and if there is an I here such that the subset is small, SI subset is small, smaller than that L we had before, right, that then the case 1 applies. So if there is an I such that set SI is smaller than L, then your case 1 will give you problem in the no instance. So then CSI on the no instance is 1 with high probability, right, which means that clique function is also 1 with high probability. Well, because clique is an OR of these CSIs. So if one of them is 1, the whole thing is 1, right. So that's a contradiction. So this cannot happen. Let's look at the other case. So for all I, the subsets are large, which now means by case 2. So now since the indicators are large, you can apply case 2 on the yes instances, right. So there is a problem in the yes instance. So the probability on the yes instances that CSI is 1 or is 0, right, this probability we calculated to be quite high. So we had 1 minus n to the minus root k by 20, that's the probability, which means that probability on these graphs of your indicator being 0. So function clique is 0 when all these indicators output 0. Each indicator outputs 0 with this much of probability, right. So you multiply them. right. So this is 1 minus 1 over r to the r, which is more than 1 over e. Where r is just this, n raised to root k by 20, and m was picked to be smaller than that, equal to that actually. So with a decent probability actually on the yes instances you are getting 0, which means that it can't be Clique function. So that's also a contradiction. So this finishes the proof. So this means that Clique Kn is not CSI. So we have shown that if you use only n raised to square root k clique indicators, then you will not be able to compute clique exactly. Okay, so it's a statement about exact computation. Remember, it's not approximation at this point. So to exactly compute clique, you do need more than n raised to square root k clique indicators. Next lemma that we want to show is to do with weakness of the monotone circuit model with respect to clique indicators. So we show that a small monotone circuit can be approximated by an OR of few clique indicators. Okay, so here we will talk about approximation, and we will show something opposite to what we showed for the Clique function, that even few indicators fewer than n raised to square root k by 20 that we had before, fewer than that many clique indicators are enough to approximate a monotone circuit. By the way, this will not be on all input instances. Okay, so this will be on the same input instance distribution as in lemma 1. Okay, so this actually result is not strong enough to work for all inputs. So maybe we should remember that. I should remark that for distributions yes and no, this is important. So let us compute the probabilities on these distributions, and also we have to specify what indicators, which clique indicators will work. So lemma 1 was about clique hard. This is now about monotone circuits. So this will show that again same k, n to the 1/4. So k is the setting is the same as in lemma 1. K is n to the 1/4. You can think of that, and size you can think of as n to the square root k by 20. Okay, similar parameters, same parameters in fact, like lemma 1. Then there exists m subsets or clique indicators where m is smaller than this. And these indicators, so subsets S1 to Sm of 1 to n, such that now we will talk about success. So we want to show that these indicators will approximate the monotone function well, or the monotone circuit value well. So actually the probability now is large of success. So on the yes instances, when you look at this OR of clique indicators, these M clique indicators, it is actually so on the yes instances it's actually 1, or it is whatever the circuit was outputting. Okay, the value of the circuit, monotone circuit C on this G. So it may be outputting 0, it may be outputting 1, but whatever it was outputting, the OR of the indicators is at least that much. It matches the answer of C with high probability on most of the yes instances, okay, according to the distribution. And symmetric thing on the no input distribution. So for no instances, this indicator is at most the value of the circuit. So if the value was 0, this is also 0 with probability 0.9. If the value was 1, then the OR of indicator can be 0 or 1. But the point is that it matches the monotone circuit C value. Okay, so on the yes instance, in 90% of the cases it is, so if CG is 1, then this OR of indicators will be 1. If CG was 0, then it can be 0 or 1. So when it is 0, it is at least matching CG. If it is 1, then it is matching the yes instance. Okay, the correct answer. So either it is the correct answer or it matches CG with high probability. So the point is that with respect to clique, we have shown that monotone circuits are approximable. That is the point. So easy with respect to clique distributions. That is what this lemma is saying. It's not a general result for monotone circuits. It's only for the clique problem. So the function that we are interested in is the clique function, and the input that we are interested in is only y and n instances. Okay, only then this thing makes sense. Okay, so how do you show this? Or maybe we will first prove the main theorem using lemma 1 and lemma 2. Okay, so proof of Rasborov's theorem. So now you see that if there exists a monotone circuit C of size smaller than what was claimed in the theorem statement, computing of course clique, then by lemma 2 there will be clique indicators. Such that the OR of them mostly agrees with the clique function for the yes and no instances, right? Because lemma 2 talks about both. So graphs both in the yes and the no input distributions, the clique function is being well approximated. 90% of the cases it is correct with this OR of clique indicators. So this is the approximation result you get for clique by lemma 2. But now go to lemma 1, right? In lemma 1, it was shown that whenever OR of indicators agrees with clique, there has to be a lot of indicators. So compare with this probability that you got, error probability of 1%, right? So the match cannot be more than 1%. That is what lemma 1 said. But by lemma 1, the error is at least 99%. So which implies a contradiction. That's a contradiction, right? So lemma 1 and lemma 2 contradict. So lemma 2 is saying that clique indicators, M of them, are agreeing with clique on 90% of the cases. On the other hand, lemma 1 is saying that they can agree on at most 1% of the cases. Okay, so it's a big contradiction, which means that monotone circuit of this much size it can't exist. Okay, so that's the impossibility result. So if once we have shown lemma 2, then lemma 1 and lemma 2 together prove Rasborov's theorem. So next time we will do lemma 2.